We're going to continue our work on aircraft performance today by looking at an example where the altitude is changing. So we're going to do the piston engine aircraft at 3 different altitudes. So we're going to plot power required and power available versus velocity at sea level, 10,000 feet, and 20,000 feet. And so what we need is the density So we've been doing all our examples at sea level, at that density. And we're going to add $10,000 feet and 20,000 feet calculations. So the process is just as normal, that we want to plot power required. So that's thrust required times velocity. And to get thrust required, it's equal to the drag. It's CD Q infinity S. So we have to calculate Q infinity and CD. And then CD is CD0 plus CL squared over pi E hat AR. So we need the lift. And the lift is the weight divided by the dynamic pressure times the area. So we work, spreadsheet-wise, we work backwards up like that, where we'll calculate Q infinity. That's where the density comes in. And then we just keep calculating up this way. So the numbers that we need, we'll need the density for that. We need the weight. For that, and then we need the formula for CD. E hat is 0.8, and the aspect ratio is 7.37. So for CL, we'll take the weight, divide it by Q infinity, and then we need the wing area, which is 174. Kind of did that backwards. So CL is 2950 over Q infinity 174. And then everything feeds up. And then the power available is given. We calculated that last time. It's the efficiency times the engine horsepower, and then we convert it to foot-pounds per second by multiplying by 550. And remember, this is the propeller efficiency here. And we'll ratio this by the density that we're at divided by the density at sea level. So if we're at sea level like we were last time, then this is just 1, and that's the number we get. if we're at, say, 10,000 feet, we plug this number in here and the sea level density here, and that ratios this sea level horsepower to the right altitude. So let's do the spreadsheet. So this will be our velocity column, feet per second. And we'll vary that from 60 upward, and we're going to do it by steps of 20, just like we did before. I went too far. We only want to go up to about 300 here. And then here's our dynamic pressure. So it's pound force per foot squared. And then we want a column for CL and CD. And then the thrust required in pounds force. Of course, that's going to be equal to the drag. And the power required in foot pounds force per second. And then we're going to do power available. I'm going to put sea level just so we keep track that this is all done at sea level. We could write sea level on all of these headings, but that gets kind of redundant. So this is how I'm going to keep track. So the dynamic pressure is equal to 0.5 times the density times the velocity squared. So that's nothing new. We've done that before, right? And then CL is equal to the weight. So that's our formula on the board there, 2950 divided by the dynamic pressure times the wing area, 174. So I'm doing that formula I wrote on the board. And then CD is the drag puller that we wrote on the board with the numbers in it. So CD0 is 0.25, and add on to that CL squared that we calculated, divided by pi times, and then E was 0.8. The aspect ratio was 7.37. So again, that's just the formula that we had on the board. And the thrust required is equal to the drag coefficient times the dynamic pressure times the wing area. And the power required is the thrust required times the velocity. So we got that. Then the power available is that the horsepower times the propeller efficiency times the conversion factor. And we don't have to put the density ratio here because it's sea level. All right, so that's similar to what we did before. Now, how do we change that to go up to altitude? I'm going to copy and paste these, but then we're going to have to adjust. Because this formula here, the v squared doesn't point to the velocity, it's pointing to g, which is just the previous column, because that's over here. We pointed to the previous column, so we have to go through and edit this to be the A column. And that's just because when you cut and paste, it references the column that we referenced before in the same sequence. We could have done the $ thing, but I think it's easier just to go through and edit it. Let's see, CL is okay because it doesn't reference anything. CD is okay because it's referencing the correct cell before. Thrust required, same thing. It's going to take CD. It's going to grab Q infinity in the right spot. So we just have to double check these formulas. And let's see, I've got something that's not right. What's going on here?
So you're keeping your density constant right now?
No, that's the problem. I haven't changed my density yet. So in this Q infinity formula, I have to change the reference to the velocity, and I also have to type in the new density. So I use my density at the new altitude. What did I do wrong? Too many double O's. 00175556. All right, that looks better. So again, this formula, I had to change the point to the correct velocity reference. And then I had to change my density because we're at altitude. And then CL, CD, thrust required, power required. Now I'm going to have to change this because it points to velocity. So it's pointing to the wrong column. So I have to change that over to the velocity. So now I have my new power required. And then I need to adjust this because this is at altitude. So I have to ratio this by the density at the altitude, 0.0175556, and then divide by the density at sea level to get my new power required, or power available. And notice it went down because there's less air, less oxygen. So that's why we ratio it. All right, does anybody need to see any of these formulas again? I know we went through these. Again, the better reference is to copy the formulas off of the board because that's all I'm typing in is that Excel version of that formula. But questions about how to type anything in Excel here? And then we need to do the next altitude. So we're just going to repeat the process that we did. We're going to grab these cells and copy them over here. 2, 4, 6 of those. And I have to go into the dynamic pressure here. Remember to change my density this time. 1, 2, 6, 7, 3. I'm going to copy that into the paste buffer because we're going to need that in a minute. And then I need to change the velocity reference here to back to column A. CL formula is good. CD, the formula is good. It's referring back to CL for the CL squared in the numerator. Thrust required is okay. This, I've got to refer back to the velocity column instead of the previous column. And then the power available at sea level, I've got to change this density to that density that I put into the pace buffer, which is the current altitude density. And I want to change my heading here, which I forgot to do earlier. This is at 10K, and this is at 20K. And that's just to keep track of what's what. Okay, does everything look okay? I'm double checking it against a spreadsheet I did earlier. Again, if we're doing homework and we're doing this for the first time, we hand calculate everything in this row to make sure that it's right. And now we can propagate this downward. And that gives us the power required and the power available versus velocity. So I can select column A and then control select all of these other columns and do a plot. So we can see power available and power required versus velocity. And so notice at different altitudes, we get different maximum velocities. The maximum velocity, again, comes from the intersection. We got to get the right curve. So we got blue versus orange. So Vmax at this altitude is here. And then we got gray and yellow. So our Vmax at 10,000 feet is here. And then at 20,000 feet, it's this intersection here. All right, so that's how you do the altitude effects. Questions before we move on to climbing flight? Because if you're going to be at 10,000 feet and you do a takeoff at sea level, we got to analyze the climbing performance of the airplane. So I'm going to jump out of this spreadsheet for a bit. We're going to add more to it once we do climbing performance. So the rate of climb depends upon how much extra power you have. Right? We've been plotting power required, and unless you're at your maximum velocity, you have extra power. Your power required curve is lower than that straight line across. It's the available power. So we can use that extra power to not just fly straight and level, but we can climb. And it's as simple as that. You calculate the excess power, and that gives you your rate of climb. But I need to show you why that's true. And for climbing flight, we need to redraw our free body diagram and include climb. So our theta is going to be non-zero. So we're going to go back to our more generic version. Again, we're not gliding, so I'm going to do theta pitched up again. So draw your horizon across like this. And draw the airplane up like this. So there's the reference chord line of the airplane in the wing. The velocity vector doesn't necessarily, usually it's not directly along that because this is the angle of attack, alpha, and there's V. So in the other frame of reference where we're sitting on the airplane, we see the air coming in like that. And then this is our flight path angle, theta. So lift, as always, is perpendicular to velocity, and drag is parallel by definition, and weight is perpendicular to the horizon. So we have that. And we want to resolve the weight into perpendicular and parallel components. So this is the angle theta. This is W cosine theta, W sine theta. So this is that free body diagram we've drawn before. But I wanted to look at it again. Oh, we got thrust on here. And for climbing flight, we're going to assume that the thrust is pretty much lined up with the velocity vector. We had that alpha t. We're going to assume alpha t is approximately such that we just line up here at 0. And we did that for the cruise flight as well. Now, if you're doing a really steep climb angle, that may not be true. Depends on how the airplane's designed. All right, so we're going to write equations just like before, but let's look at the picture. Because we can, this is not so complicated that we can't just look at the thrust, the force balance ourselves. It looks like lift is going to balance out W cosine theta, so it's going to carry part of the weight. But thrust has to counteract the drag as well as that W sine theta part. So there's part of the gravity vector acting backward in this case. Now we used that to our advantage in gliding flight where we dove down, and so the gravity vector actually provided the thrust with the power off. But in this case, to climb, we've got to counteract gravity with some of the thrust. So the key takeaway of this picture is that the thrust has to balance part of the weight. And in fact, the steeper you climb, the more of the thrust is used to balance the weight, not just the drag. And that's why you need the extra power or the extra thrust to climb, is because it has to balance part of that weight vector. In fact, if we're climbing totally vertical, the thrust has to equal the weight, right? And you don't need any lift at all. All right, so some of the forces parallel is thrust. Again, we have that cosine of the angle here, but we're saying that that angle is pretty small. Minus the drag backwards, minus the weight, sine theta, and that's equal to the mass times the acceleration. But we are still doing steady state flight, that is an unaccelerated flight. So this is 0. So we probably had to put that. This is rate of climb, unaccelerated flight. Because it's a totally different deal if you want to climb and accelerate, that is, make them go faster and faster. And I don't think we'll get to it today, but I'll show you some overheads about the F-15 setting a record to climb to 100,000 feet. And it has so much thrust that it essentially was a rocket, but they did a special flight path where they took off and then actually accelerated past the speed of sound as they climbed to altitude. So it's pretty impressive. So that's the force balance there. And then the sum of the forces, I should have put F there, so sum of the forces perpendicular are lift minus W cosine theta, and that's equal to the mass times the velocity squared over the radius of curvature of the turn, but we're not doing a turn, so we really ought to write that up here. Unaccelerated flight, straight line flight. So performance, as far as maneuvering goes, is pretty boring. We're flying straight, we're either going level or going up or we're going down. But these are important things so that we know, well, what is the performance of our airplane? So the two equations that we get are thrust equals drag plus that weight component, and lift equals that. Now the upside is that the lift doesn't have to be as high as for straight line flight, but that's because we're using the thrust, which is less efficient than the airflow to produce lift. All right, so we want to talk about rate of climb, which is, we've already introduced the concept, it's h dot. When we did the gliding flight, we talked about time aloft is minimum sink rate, which was negative h dot. So now we're talking about positive h dot going up. So again, the big deal is that the thrust has to counteract part of the weight. And if you draw that picture carefully, you see that directly from the picture. All right, so to get the rate of climb, we need a velocity diagram. And it's something we did for gliding flight, so this is nothing new, except now our velocity vector is going up. And this is the angle theta. All right, so I'm just grabbing that one small part of the picture we already drew. And this is our ground speed, assuming no wind. And then this vector is our vertical speed, or what he calls rate of climb. And that's just the velocity vertical. That's how fast you're going up away from the Earth. So from this, it's really easy to know that the rate of climb is the velocity times the sine of theta. And that's the same formula we had for theta hat when theta was pointed down, and we said negative h dot was that. All right, so we want to get this formula in terms of the lift and the drag and the weight from over here, because this is the stuff we know how to calculate, right? We can calculate CD and we can calculate CL, and we want to put that into that formula. And we're seeing a sine theta here. So in fact, that's how we're going to do it. We're going to walk through the thrust required, which is going to be this value here, and look at it compared to the power available. So this formula here gives us the thrust required to climb at an angle theta at a velocity v. Because the velocity is going to go into there when we calculate CL and CD. So we're going to call that thrust required for climb. And then the power required, we already know how to calculate that. So we're just saying for climbing flight, there's how much thrust we need at any given theta and any velocity. And we've been calling this V infinity, so let's put V infinity here because it's more consistent. Okay, and then we plug this in so we get D times V infinity plus W V infinity sine theta. And then we know that we have a certain amount of power available. Either directly calculated, or if it's a jet, it's thrust available times V infinity. And so we look at this and we say, okay, here's how much we need to climb at, say, 10 degrees at 100 feet per second. And we could start tilting that theta up 10, 15, 20 degrees. And this power required, thrust required is going to increase because we need more and more thrust the steeper we climb. So we're going to say, well, what happens if we just go full throttle? How fast can we climb at a certain velocity when we keep tilting the angle up until we need all the thrust we possibly have? And that occurs when the power required equals what's available. In other words, we crank the throttle all the way up to where what we need is what we have. Make sense? So you're flying along straight and level, you need the throttle set at a certain level. You tilt up to 10 degrees, you got to increase the power. You increase to 15 degrees, same velocity, got to increase the power. And finally, you reach, say, 17.8 degrees, where the throttle's all the way in, and that's all you can do. You can't go any steeper up, because otherwise you're going to start losing airspeed, because your forces aren't balanced. So the full throttle rate of climb is when the power required is equal to the power available. Now your book just calls this the rate of climb, and I think that's a little confusing because you can climb at any angle and you don't need all the power. So I like calling it the full throttle rate of climb. So that means we just set these things together. So the thrust available is equal to the thrust required, which is so that's the equations of motion for full throttle rate of climb. And you can see that we're going to get the rate of climb in here. But let's rearrange this equation a little bit because it helps. Pull this drag term over here and then divide by the weight, because then we've isolated H dot exactly. And this formula tells us how to calculate the rate of climb full throttle at this given velocity. Again, the angle is determined by, we just keep tilting up until we using all our power. So that's why we set those equal. So let's write that formula up here. Because that's the formula we'll use in a spreadsheet to calculate the rate of climb. And we know that the throttle of the thrust available or the power available, it goes down as we get up in altitude. So eventually H dot's going to get smaller and smaller. And sometimes it's convenient to write this as this instead of thrust. And the reason I do that is notice that this drag times V infinity is the power required for level flight. Because if we go back to when we were talking about level flight, that's what we need. It's just the drag times V infinity. Because in level flight, we're not tilted up. And so the thrust or the power required is the drag. Well, why do we care? I mean, we could just calculate this. Well, it turns out that if we recognize this, then we've already calculated everything we need in the spreadsheet already. Because on the level flight spreadsheet, keyword, make sure you like box this. So don't think the power required for climbing is the power required for level flight. It's a different deal. But that formula matches for level flight. We go back to our spreadsheet and we have the power available already in a column, and we have the power required for level flight already in a column. So all I got to do is add this little extra calculation and we're done, instead of doing the whole spreadsheet over to do this part. So after 15 minutes of talking here, hopefully it was coherent. I hope it was. It's really easy to do this because we figured out how it's all related to level flight. So let's see, yeah, so in fact, graphically, it's easy to do. Oh, and I wanted to say one more thing. So this is what they call excess power. Because it's the extra power you have available compared to what you needed for level flight. And you can use, that's what I was talking about, you can use that extra power to climb. And that's really all we're doing. And we just have to remember that this is really full throttle. You don't have to climb.
Does that mean you can climb faster whenever you're closer to sea level?
Yeah, because you have more excess power because there's more oxygen. That's even true for you as a human, right? There's that crazy marathon where they run from the base of Pikes Peak up to the top, 14,000 feet. There's less air up there. So if we have these plots that we've already done, we've plotted power versus velocity. We have our power available curve, and then we have this power required curve that we've already plotted, and that's for level flight. This rate of climb simply says you take, at any given velocity, you look at this excess power. I think I lost it. E. No, we're good. So it's that excess power. And you can see that at different velocities, that excess power is going to be more or less. If you're going really fast, if you're going at V max, you have no extra excess power. So if you're screaming along at your V max, you can't climb because you're using all your power just to go straight and level. Different velocities. And so you can see that there's going to be a spot here for maximum rate of climb, or what you would more commonly refer to as best rate of climb. So if you wanted to get to the altitude the fastest, you would fly at that airspeed because it means you have the most excess power. All right, so we're going to go back to our spreadsheet with the prop and do this. Do what?
How'd you make that so quick? That chart.
The one that I did just previous, this one that I clicked on?
Yeah.
I did that before. Yeah, you saw I did that, right? I highlighted A column and then control clicked it. Yeah, so that's, I'm just deleting it to get it out of the way. So this is back to that spreadsheet that we've already done. And we could either go in and insert here an extra column where we do the rate of climb. And then that shifts stuff over, and so we have issues with pulling the right velocity. So I'm going to add all of the columns over here. So here's our rate of climb at sea level. This is going to be our rate of climb at 10,000 feet, at 20,000 feet. And I want to watch my time. I think we can finish this off. We'll have to talk about, I'll show you how to do ceiling as well real quick. So this is exactly what you're going to be doing for homework, is these kinds of spreadsheets. So the rate of climb at sea level is equal to the power available at sea level. I need parentheses here. The power available at sea level minus the power required divided by the weight, which was 2950. So at 60 feet per second forward speed, there's our rate of climb. And again, this is full throttle rate of climb. At 10,000 feet, we go over here and grab the power available minus the power required, again, divided by the weight. Notice it went down because the excess power is less. The power available at that altitude is less. And then we'll grab the power available and the power required at 20,000 feet. And we can grab one of these and plot it. And we see that there really is a maximum rate of climb. It's where that excess power is. And so you can go through and pick off the rate of climb maximum for each one of these. So here we do rate of climb max. Sorry, I want to put that in another column here. Versus altitude. So here's our altitude in feet. So at sea level, I'm looking down the sea level plot, and it looks like the maximum rate of climb is 24.86, 85, 859. So I'm just going to type that in here, 24.859. And that's in feet per second. And then at 10,000 feet, what's our max there? Go down the column, 14.4 looks like. And then at 20,000 feet, maximum rate of climb is about 5.434. So this shows us how our best rate of climb varies with altitude, and we can do a plot for that. So again, there's nothing magical here. I just picked the maximum rate of climb for each altitude. And we look at the trend and we see sea level here, go down to 10,000 feet, our rate of climb goes down. 20,000 feet, it goes down. It looks like at some altitude, our rate of climb is going to go to 0, isn't it? It'd be nice to know what that is, because that's essentially the maximum altitude we could gain in this airplane. If we can't climb, we can't go any higher. And in fact, that's what is called the ceiling of an aircraft. And so to find the ceiling, we simply extrapolate this line. You can take this and add a trend line, and we'll do a linear trend line. You guys done this before? What I did was I clicked on the series of points, and then I right-clicked and picked trend line. So let me show you that again. So here's our series of points. I'm right-clicking, add trend line, and then I choose linear or whatever. So I'm choosing linear. And I can tell it to extrapolate forward 5,000 feet, because that looks, we could go further, we could go 6. And I can even display that equation on the chart. And then I can use that line to look at this, and I go, oh, well, the maximum altitude, the ceiling is about 26,000 feet. And so that's what a ceiling is. Now there's something called a service ceiling, because all you can do is asymptotically approach this absolute ceiling. Because as you get closer and closer and closer to the ceiling, your rate of climb goes lower and lower. So really, you'll reach a point where it might take you the next 10,000 years to actually get all the way up to that, and you'll run out of fuel before then. So there's something called the service ceiling, where the rate of climb is 100 feet per minute. And we'll do a little bit more with that in time to climb next time on this. But I wanted to define those so that you could work that final part of the homework. So the absolute ceiling, let me switch back. Sorry, we're going a couple minutes late here. Is when the rate of climb max is 0, and the service ceiling is when the rate of climb max is equal to 100 feet per minute. Notice the units here, we're doing in feet per second, so you have to multiply by 60 to get feet per minute. And that's all there is to do with ceiling, is you calculate these rate of climbs, and then these are the definitions of those values. And that's where you stop in the homework. Is you'll do the spreadsheet just like we did for the power available, power required, and then you'll calculate the rate of climb, pick off the max, and plot it versus altitude, and you're done. All right. Hopefully you've started on most of this, right? We've had the tools to do this up, pretty much up to the thrust available, thrust required, power available, power required. Again, let's see, this is due, I pushed the due date back to a draft spreadsheet to Blackboard by Wednesday. You don't have to have it completely right, but do enough of the spreadsheet so that I can see you actually worked on it. It's a draft. Complete as much as you can. Go through the ceilings, but by Friday you need the final. So you're going to submit 2 spreadsheets. The draft on Wednesday, and then your final that's going to be graded on Friday. This Wednesday, this Friday, yeah. And then we'll do a quiz on Friday, just like normal. So we'll go over these problems on Wednesday, but again, I'm forcing you to get ahead on it and do the spreadsheet because I want to see that draft on Wednesday. I'll let you go, we're over, and I apologize.
I had a question about the project. So whenever we're deciding like the surface area of the tail and the vertical and the horizontal tail, how do we go about optimizing that? Because it seems like there's not really any like equations that kind of.
Yeah, in this class, we really don't. there's not a whole lot you can do with that. So just, you know, make it look good.
Right. Okay. So whatever kind of looks normal for industry.
Yeah.
Area, and then try that.
Yeah.
Okay.
I mean, you can go wild and do, you know, a little tiny tail really far back, but then your fuselage is long.
Yeah.
So you just, go based on what airplanes look like.
Okay. And we should try and optimize the fuselage diameter and length in order to make it so that the coefficient of drag is as small as possible.
Yeah.
Right?
Yeah.
Okay. I see. The diameter is kind of defined by the pilot almost.
Right. So the pilot obviously has to fit in the fuselage.
Okay.
And that'll be part of what you'll show in your presentation is, here's my fuselage, here's how the pilot fits in there, you know, and the pilot will talk about, well, the ergonomics of, of how he's sitting in there. And
Okay.
again, you know, we can't do a full-blown design, but just do as best you can.
And fuselages aren't circular usually.
Right.